Hi, in this video, we want to take a look at hierarchical clustering with Python. Specifically, we're going to be using the scipy package. All right, now, so within scipy, we need to go to cluster, then hierarchy to perform hierarchical clustering. Now, why do we do clustering? Well, for clustering, we have several reasons. First one would be we're interested in segmenting our data. So we want to break up our data into smaller groups where the data in each group is more similar to each other than data points in other groups. Outlier detection, subpopulation detection, and then feature engineering. All right, so these reasons are common to all types of clustering. Now, with hierarchical clustering, we could also be interested in taking a look at the taxonomy built by our clustering to gain insight into similarities with our data. All right, so remember, when we go through this process, I'm taking numeric data and I'm grouping by the rows of the data. So variable clustering is similar but different. In variable clustering, we're clustering on the columns. Here, when you just say here clustering by itself, we're going to be talking about the rows. All right, so in hierarchical clustering, we have to make two choices after we have our data prepared. We have to choose what is our distance going to be. That is, how do we decide how far two rows of data are from each other? And the second one we have to choose is we have to choose the linkage. All right, with the linkage, that is the algorithm for deciding which data points are in the same group. Now, the output will change depending on the choices I make with this. And so I need a distance, and that gives me my distance matrix. So if I have 100 data points, I'm going to have a 100 by 100 distance matrix. Then I'm going to pass that distance matrix into the linkage algorithm, and the linkage algorithm is going to build up the taxonomy and thus give us our clusters, our groupings. Now, when I'm going through this process, let's say time is of the essence. Maybe I have such a large data set that I can't explore a lot of possibilities. All right, well, what we can do is I could run one or maybe a few distance matrices and then run different clustering linkage algorithms on that same matrix. And that gives me the ability to explore multiple models when I have a big data problem and computation time is an issue. So if we are in a situation of I don't have a lot of time, maybe it's computation not feasible, maybe I'm rushing to get stuff done, do one distance matrix and then explore multiple linkages. Now, if I have time, I'm going to go through multiple distance metrics, and I'm going to go through multiple linkages to see what's going to work out best for my project. All right, now something that can also help you is some guidance on what you should do when you're not going to run multiple, or you're only going to run a few algorithms. All right, so the first one is to give you advice on is that if you don't know what distance to use, go with Euclidean distance. That's by far the most common, and it's the one that most people will be more familiar with. Now, in terms of the linkage, if you don't know what to go with complete linkage. The reason for this is that people in the scientific community, specifically biologists, are the most comfortable with this. And so if this is, from everything I've seen with scientists involved using hierarchical cluster, every single time they've used complete linkage. So don't know what to do, just go with complete linkage and run it. Remember, our number one priority in doing data science is to get our client to have buy-in on our project. If we don't have buy-in, there's no point in doing it. So if they want complete linkage, go with it. Now, something that I've observed, I haven't not read this anywhere, I haven't seen this in a YouTube video or anything like that, but something I've observed is that Ward's linkage does a better job of giving approximately equal size clusters. And single linkage does a better job of outlier detection. Single linkage, you'll be prone to having a cluster of size 1, which is possibly an outlier or an anomaly that we want to check out further. So if you don't know in terms of distance, go with Euclidean distance. If you don't know in terms of linkage, go with complete linkage. If you're looking to have approximately equal size clusters, then go with Ward's linkage. And if you're doing outlier detection, go with single linkage. All right, so let's go ahead and run through some examples. You know, in my video series, it's all about getting real data and actually executing the code. So everything you see is code that I ran on my machine. All right, so here is some data from the City of Orlando's webpage. This is part of their open data project. This is the Orlando Police Department's officer-involved shootings. Now, this is only for Orlando Police Department. This will include like Orange County or Seminole or Osceola County. No, this is only for the City of Orlando Police. All right. When we do this type of clustering, we are strictly using numeric data. So I'm going to pull out only the numeric columns, and I get my data set. And we can see the data set. We can see that there's definitely some data prep that needs to happen. You got some strings, got some multiple values in the same cell. So I'm going to go through. All of this is just dealing with those issues. This is taking the median of a cell when there's more than one entry. And then this part is filling in missing values and string entries with the column median. And so now we have that all cleaned up. Now, when we do clustering, if I do partition clustering or if I do hierarchical clustering, I need to make sure that I have an idea of what's going on with the scale of my data. The columns with the most variance or the most standard deviation are going to be the columns that have the most influence on my cluster model. If I want each column to have equal influence, I need to do something about that. In scipy, we use the whiten function. The whiten function sets it up so that we have the same standard deviation for each column. And so here I'm just running the whiten column to make sure that all columns have equal influence on my model. And so here we can see that each column after I do whiten has a standard deviation of 1, approximately speaking. All right, so now that we've got our data prep, we need to go in and actually do our hierarchical clustering. So remember, there's 2 steps to this. There is the distance matrix computation. Then the second step is actual clustering algorithm, the linkage. All right, so we have to make 2 choices. I need to choose a distance and I need to choose a clustering. How we're going to proceed is that I'm going to compute a distance matrix, and then I'm going to pass that distance matrix to the linkage function. And if you don't know, use Euclidean distance, the default distance, and use complete linkage. And if you're crunched for time, do fewer distance matrices and do more linkage explorations, if you can, if that's an option. All right, so when I do my distance matrix, we're going to use scipy once again in the distance portion of the functions, and we're going to use pdist. Okay, so if I have 100 data points, I'm going to get a 100 by 100 distance matrix. That's actually not quite right, because conceptually it's going to be 100 by 100 with 0 on the diagonal. Well, a distance matrix is symmetric. So the upper triangle and the lower triangle of the distance matrix are going to be the same. And the diagonal is going to be all zeros. So in fact, I don't actually need all of this. What I only need, I just need the n choose 2 upper, or no, yeah, the n choose 2 upper triangle values of the entries. And from there, I could fill in the rest. So what we're going to do, if we have a 4x4, we're going to end up computing 5 different values. So, no, 6, sorry. We'll compute 6 different distances on there. We're not going to produce a full proper distance matrix, even though mathematically they're equivalent. I can go back and forth between them. All right, now when I make my choice on the metric, I have all these different choices. I have tons and tons and tons of choices to go from. If you don't know, go with Euclidean. All right, so there's plenty of these here. I've played around with all of these. I have used professionally. I've used city block. I've used correlation, cosine, Euclidean. Now, Hamming and Jacquard I've used with string distances, but not with numeric data. And the rest, I've touched a few of them, but overall, honestly, most of the time in my experience, you're going to want either city block, that's called the Manhattan distance, the L1 distance, or Euclidean L2. I just, personal experiences, those have given me the best results. Oops, I didn't mean to do that. All right. Now, there are some additional arguments that we can pass if we're doing other ones. So if we're using Minkowski, we can set the P norm to it. So if I want a norm other than 1 or 2, I'm going to go to the Minkowski, and let's say if I want 3, 4, 5, anything like that, I'll go, with Minkowski. Here, if I want to start altering the weights, I can go with the W parameter. Oops. That's not what I want. There we go. And we can change different values here and there as needed for different metrics. All right, so let's go ahead and run this. Now on my machine, this distance did not run on my personal machine. It threw an error. The rest of these did not give meaningful results. The Yule, the Dice, the Roger Stanley Moto, Russell Rao, and these did not give me meaningful results. So I went ahead and just commented them out. So they're not polluting the rest. The rest of these ran on my machine. Yeah, the ones that I strongly recommend are Euclidean, then city block, and then possibly correlation or cosine. I could see like all those being good first choices to go with. All right, now when we do this, when I get my result, now you'll notice that I did this as a for loop. I created a dictionary. So I went through and computed a distance matrix for each of these on the same data sets. And so if I was working on a real project, I would do multiple distance matrices and I would run multiple linkages on each one to choose which one looks the best, which one I feel most comfortable with. So here, how I like to proceed with this, I like to have all my matrices, all my distances, everything in one object in my workspace. It keeps things cleaner and I can iterate over those items to be able to execute very clean code. And so here, I'm just going through and I've created a dictionary. So here I define the dictionary and I'm just saying that for each of the different metrics, compute the pdist on my data, and here the J is what I'm iterating over as the metric. And so now we can see the outputs. So you'll notice that this is presented as a straight line. So what's happening is that these values by position, Python knows where to put each of these to reconstruct the distance matrix. It just stores them in this manner for us, when we look at it. And so here is the Euclidean one, so that we can see it, what it is. And if I want to make this into square form, so if I use the square form function within scipy, this is going to actually set it up so I can see what the actual values look like as a distance matrix. And so I can see here I have a 0. This is the distance between the first row and itself. This is the distance between the first row, second row. This is the distance between first row, third row. Keep on going. This is the distance between the first and last rows of data. And I can also go down this way. And so you'll notice that I see the same value here as I do here. I see the same value here as I do here. I see the same value here as I do here. Just keep on going. See this one here. So in this format, every entry off of the diagonal is presented twice. And on the diagonal, I have a 0 every single time because the distance from an observation to itself is always 0. All right, so this is redundant. This takes up more memory than it needs to. This is why it's stored under the hood in this straight line manner. All right, so now let's take a look at the different linkages. All right, so here we can go single, complete, average, weighted, centroid, median, or ward. Single linkage does a good job of outlier detection. Complete linkage is, from my experience, from what I've read, the most common for science. It's also a good default choice in general. Ward does a better job of giving like more similar size groups when I do my clustering, and the rest are somewhere in between ward and single linkage in my experience. And once again, I'm going to go through the same process. I'm going to go ahead and run my linkage. Here is my method that I'm going with. Here is the distance matrix for me. Now it's stored in under the hood format, in that straight line format. And this optimal ordering, I'm putting this into true. Optimal ordering will set up so it's easier for me to interpret when I look at what's going on. The disadvantage of this is that this will slow down the computation. So if I'm in a big data problem, I might want to put that down to false. Optimal ordering will make it easier for you to interpret what's going on, but it will take longer. There's a price there. You gotta make a choice. Here, small data, I set it to true. All right, so let's go ahead and take a look at the Euclidean distance and complete linkage format. All right, so the Euclidean method or metric determines the distance between rows. The complete linkage determines which rows of data are in the same groups and forms the taxonomy. And so here is the array of how the dendrogram is coded. And we can see that there's a lot of stuff going on here. We don't really need to know anything about this. I just want you to know what it looks like. All right, so let's go ahead and actually plot what this looks like, what our model is like. All right, this first one we're going to look at is Euclidean distance with single linkage. The first thing I want you to notice is that here I have, this is saying that there is one, so how to interpret this? you come along to a spot and you cut the tree vertically. So I have a orientated right. In my plotting, I put orientation to right. So the default setting is to have the tree coming down like this. To make it easier to read the ID numbers, I put orientation right. Now, when I look at this, what this is saying is if I come up and vertically chop on my tree, this is saying that this one point, this one row of data is by itself. All of these others are in the same group. So if I cut here, I'm going to have two groups. This one is by itself, and all of the others are in a different one. So here, that leads me to believe that this is an outlier. In fact, that is the Pulse nightclub shooting, unfortunately. So there we have, it's definitely an outlier. This verifies that this does a good job of doing outlier detection. Now, if I cut here, we're going to see that we're going to have three groups. Well, in these three groups, you can see that this blue leaf is by itself. This blue leaf is by itself. Now, everything else is in its own group. All right, well, that leads me to believe, well, maybe this one from 2018, that might also be an outlier. I don't know. Not as extreme as an outlier as the Pulse nightclub shooting, but that's one I would definitely want to take a look at. If I cut here, I see that I have the Pulse nightclub shooting by itself. This other point, which is like my second candidate for an outlier, and I have here, this one looks like it's by itself. And this is from a 2021 incident. That's by itself also. So now I think I have three outliers going on. And when I look at the rest, everything else is in the same group. All right, so these three at the bottom are the three that I want to check on my data to see maybe there was an error in the recording. Maybe this is a special event. Maybe I should omit this row of data. Maybe I should change some entries depending on what I'm doing. So like if I was modeling, the Pulse nightclub shooting at the time was, the most deadly shooting event in the United States up until that point. Probably want to pull that out of any modeling I would be doing because it's just so extreme from the rest. Now, the next one we'll look at is complete linkage. Now, complete linkage, you'll notice that once again, we do get those same two are off by themselves. So, this is picking up, some outlier detection for us. But you'll notice that if I slice things, I'm getting like more even-ish groups. So if I was to slice here, let's say that I cut at a height of 5, then I have outlier, outlier. Now I have a small group from slicing here. Everything, all of the values that come off of here, off of this blue one that turns to orange, they're all in one group. I come to here, I see that these greens are all in the same group. Cutting here, we see that all of these leaves that are green are in the same group. And then everything else is in the same group. So we would have 1, 2, 3, 4, 5, 6 different groups, 2 of which are off by themselves. So complete linkage is doing the outlier detection for us, but it's only detecting 2. And we're getting kind of lopsided, cluster sizes. Now let's take a look at the Ward linkage. At the Ward linkage, so when you look at this, you'll notice that things seem more even. All right, so we can find our outlier already. Easy to spot there. But let's say I was to cut maybe about here. Let's say I cut at 5. Then we see that all the orange are together. We see that the greens are split into 2 groups. So this green is by itself, but the rest of the greens are in a group. Here we have an outlier. And then we have a small group of 3 coming up. If I cut here, I trace down, all of these are into a group, and keep on coming up, we can see this is a group and this is a group. Of the three that we've seen, the size of the groups is more constant than with the others. And that's something that's nice about the Ward D. Ward D works to minimize the standard deviation when it's running the linkage process. All right, well, that's all I've got for you. Take care and goodbye.